Hey everyone, in this lesson, I will show you guys kind of like a little trick. Um, it's a shortcut. It is called factoring difference of two squares. So um, when we have two things that are squared together, right, which a lot of the stuff when we're talking about quadratics is to the power of two, meaning squared. A lot of the times when stuff is squared together and it's subtracted, there is a way for us to factor it out or undo the multiplication of those things a really quick and easy way. First, I'll show you like the normal way that you probably could already figure out how to do in an example. And then I'll show you guys a shortcut in which we can use from now on to figure out if we have a difference of squares, how do we factor that out? So first, let's start off with the definition. So when you're factoring a difference of squares, again, factoring means undoing the multiplication. We've talked about that before, right? So we're expanding it out into two binomials multiplied together with each other. And this is a shortcut to factoring trinomials when the middle term is zero for a quadratic. And I'll show you guys the long way in a little bit. But first, since we're talking about squares, that means that we're literally talking about squares. So let's go through some examples of some things that are squared using restroom tiles. So these are actual pictures of tiles from random restrooms. So this is an example of 3 to the power of 2, which is 3 squared. It is called 3 squared because if you notice, it forms a square. There's actually 1, 2, 3 on this side, so the total is 3. And then there's 1, 2, 3 on this side, so the total is 3. When you multiply 3 times 3, you get 9 tiles. And if you actually count this out, you get 1, 2, 3, 4, 5, 6, 7, 8, 9 total tiles. So this is another way of saying area, basically. You guys have talked about area before, so it's kind of like the same thing. This is another example, 4 squared, which is 16 tiles. There's 4 tiles on this side, 4 tiles on this side. If you actually count out the total tiles, 4 times 4, count them all out, you get 16 total tiles. This is the area that's on the inside. You could also do the same thing. I have one more example. If you have 14 tiles on one side, 14 tiles on the other side, you could actually count every single one of these individual tiles one by one, and it will give you a total of 196 total tiles. But again, math, the reason why we use math is to make predictions and take shortcuts. So that's exactly what we're doing here. 14 times 14 would give you a total of 196 tiles inside of this square. So when we're talking about squares, we're literally talking about squares because when two things on opposite sides of each other are the same number, it creates a perfect square. Doesn't matter what that number is? No, it doesn't. For example, would you agree if I said that this is a square? So we have on one side, we have x plus 6. On the other side, we have x plus 6. Do we really need to know what x is to know that this is a square? Not really, because it's the same number on this side and the same number on this side. So if x is equal to 1, then it'll be 7 here and 7 there. If x is equal to 2, then it will be 8 here and 8 there. So it'll still make a perfect square no matter what. So essentially, this is basically the illustration of a square in binomial form, which you can actually write out as x plus 6 multiplied by x plus 6 like we've done in the past. Now, in a lot of math books, mathematicians are lazy, so they want to basically write this out as a perfect square. So they usually try to avoid writing stuff out more than once if they don't need to. So most likely in your math book, you'll actually see this as written like this. So it'll be x plus 6 to the power of 2. Because that's the same thing as that, right? That's just x plus 6 multiplied by itself, x plus 6 times x plus 6. So that's a little just about, perfect squares in general. Now, since we're talking about perfect squares, you need to know your multiplication tables in terms of perfect squares to be able to do some of these examples. So go ahead and pause this video if you need to, and you're going to need to write down and memorize up to 15 if you can of the perfect squares that we have from 1 to 15. For example, 1 times 1 will give you 1, 2 times 2 will give you 4, 3 times 3 will give you 9, so that's 3 squared, right? 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, opposite of this one, just flip the last two numbers, and then 15 squared is 225. So most of the time in basically most of the math classes that I've had in the past, you don't really get anything past 15. So I would say just for sure no up to 15. If you want to do more, that's even better. But at the very least, write down and memorize these squares, perfect squares. Okay, now that you have that, you also need to know the squared roots. And the square roots are basically just the sides of the square. So it's like we're going opposite. So the squared root of 1 is 1 because 1 times 1 will give you 1, right? The squared root of 4 is 2 because 2 times 2 would give you 4. The square root of 9 is 3 because 3 times 3 would give you 9. The squared root of 16 would give you 4 because 4 times 4 is 16. So we're going backwards. It's the exact same table as the other one, but this time we're looking at the squared roots. So the squared roots is actually like if you're looking at the side of the square. And then when you actually have the inside, would like the area portion of the square would be like the number, the big number. Kind of like what we looked at when we looked at the tiles. So if you need to write these down, go ahead and pause the video, write these down, because at the very least you need to know those two tables. Okay, that being said, so let me just take you back to one of the lessons that we had in the past. Let's say they give you in a book or in a problem somewhere, you want to factor out this polynomial. In this case, we have a binomial to the power of 2, so it's a quadratic technically, but it is not a trinomial, meaning that there's no term in the middle. It's just x squared minus 9. So if I was in your shoes, if I was a student and I'm like, okay, crap, I know how to factor this. I'm sorry, not that. I forgot the x. So I know how to factor ax squared plus bx plus c. Like I know how to do that. The only problem is it doesn't look like that. But I can make it look like that, right? If I wanted to use the big X. All I have to do is include a middle term. So what I'm going to do here is I'm going to go ahead and say, okay, this is x squared plus there's nothing in the middle for b. So I'm going to write, okay, I'm just going to say that's 0b. So there's absolutely nothing there. And then I'm going to include the negative 9. So this is the exact same thing as that, right? Except that the middle term that I have, it's actually a 0. So 0 times b is just 0 or nothing. So it's the exact same thing as the original problem. Now, if I was in your shoes and I wanted to do this, this is the long way, by the way. If I wanted to do this the long way, I would say, okay, so how would I factor that out? I would say, okay, I would make a big X. And I would say I multiply the first term times the last term. In this case, there's only one variable, so I'm going to go ahead and just multiply the coefficients. So I would say I'm going to multiply the 1 times the negative 9. I'm going to put that on top. So that'll be a negative 9 on top. And then the 0 would go on the bottom. So I'm going to put a 0 on the bottom. And that came from the b. Now, same exact thing as what we've done in the past. You want to figure out what are the two numbers that multiply to the number on top, but add to the number on the bottom. So think hard about this. What two numbers multiply to the top and add to the bottom? If you said positive 3 and negative 3, that is correct. 3 times negative 3 would multiply to negative 9, but then 3 minus 3 would cancel out and you would get a 0. So this is actually the correct combination. And then you would do your factored form. So you would actually write down ax, which is just a 1x, right? So 1 and an x would go here. And then I'm going to rewrite the 1 and the x again. You don't really need the 1. I'm just writing the 1 as a placeholder. The factors were positive 3 and negative 3. So I'm going to put a plus 3 here and then a negative 3 there. And then what number can divide by both of these? Well, nothing except for the 1. So my final answer is just that. So final answer is x plus 3 multiplied by x minus 3. Great. We've done the problem. This is basically using the method that we've done in the past, using the big X, right? However, there is an easier way to do this because if you know your perfect squares, which we have seen up here, right? So this is the list of all the perfect squares. We should know that x times x is x squared, and then 9 is actually 3 squared as well. So this is considered what is called a difference of squares, because it is one number that is squared subtracted by a number that is another number that is squared. So it's basically essentially saying this is x squared subtracted by the number 3 squared. Hence the word and the title difference of two squares. So let's go into the formula that you guys see in books and that's being thrown around in a lot of different math classes. So this is the formula that they give you guys for difference of squares. So I'm going to go ahead and ask you guys to pause this video again and then write this down, because this is a formula that's going to save you a lot of time and effort if you actually take the time to write it down and study it. So it says, if you have two things that are squared together and they're subtracted, key here is subtracted, right? That's the term difference. Then we can write the answer straight up as a minus b. So a squared minus b squared is a minus b times a plus b. Basically, there's a negative and there's also a positive. So this is just a minus and a plus. The terms of a and b stay the same. This is the exact same formula that we have down here. The only thing is, like, the order is backwards, which is not a big difference, as you saw in this class through commutative property of multiplication. 2 times 3 is the same thing as 3 times 2. The order doesn't matter when you multiply. Okay, so now what does that say in plain old English? So right here, I started for you. I put a little asterisk. If we have two squared terms subtracted, the factors are the multiplication and this. Wait, let me make a better rectangle. If we have two squared terms subtracted, the factors are the multiplication of the sum and difference of their square roots. So there is where the first two tables that I had you guys copy down come into play. If you know your squares and you know your square roots, this is going to be a piece of cake for you. Okay, for example, let's try to do a numerical verification here to see if that formula actually works, right? So this is 25 minus 9. Yeah, that's just regular 25 minus 9. If I were to ask you, what's 25 minus 9, you'd be able to tell me the answer, right? So 25 minus 9 would give you what? If you guys said 16, that is correct. So the answer for that would be 16. However, let's try to see if the formula actually works. I'm going to be using the formula for regular numbers. I'm going to say that this is a difference of squares, right? So this is a squared minus b squared, which means that here in this case, it's the exact same thing as if I write 5 squared, which is the exact same thing as 25, subtracted from 3 squared, which is the exact same thing as 9. Now the formula says if I have a squared minus b squared, I can just straight up jump to the answer of the factors. That is a minus b multiplied by a plus b. So in this case, this is going to give me the factor of 5 minus 3 multiplied by 5 plus 3. And if you actually check out the numerical verification for this, it actually does work out. 5 minus 3 would give you 2. And then 5 plus 3 would give you 8. So 8 times 2 would give you a total of 16. So this is just using plain old numbers. Now, did I have to do this? No, not really. I'm just doing this so you guys can know where the formula comes from and that the formula actually does work. However, we can use this for polynomials, which is going to save us a lot of time and effort. So, example number 1, factor the following expression. So we have x squared minus 25. Now, since I am a very smart student that I just figured out this is a difference of two squares, so this is actually x squared, right, subtracted by 25. I know that 25 is a perfect square, so I'm going to go ahead and write this as x squared minus 5 squared, because I know that that is a perfect square. Now that I have that, I know that basically I can write down the answer, because using the formula a squared minus b squared is equal to the factor of a minus b multiplied by a plus b, I can just straight up say, okay, since I know this is a difference of squares, my final factors are x minus 5 multiplied by x plus 5. No need to do the x, no need to do the box, none of that. Just jump straight into the answer. If you actually multiply this out, you would get the original problem. Done deal. Okay, so example number 2. That's all there is to it. Let's say you wanted to factor out this polynomial here. In this case, we have a binomial to the power of 2. And then we have a minus in the middle. So technically, this is a difference of two squares. Why do I know that's a difference of two squares? Because I know that I can take the square root of this and get a nice answer. And I know that I can take the square root of that and get a nice answer. To be more specific, this can actually be written down as 4x all to the power of 2 subtracted by 3 all to the power of 2, right? If I multiply this out, I would get the same thing that's on the left-hand side. So since I am a smart math student that wants to save a lot of time, I'm going to use the formula for difference of squares, which is a squared minus b squared is equal to a minus b multiplied by a plus b in any order. So therefore, I'm just going to straight up jump into the answer. I know that the answer, when I factor this out, is going to be 4x minus 3 multiplied by 4x plus 3. Done. If you actually multiply this out, you would get the original problem. So if you do the box, multiply this out, you should get 16x squared minus 9. Okay, so like I said, this is going to save you a lot of time and effort. This is called factoring using the formula for difference of squares. Okay, example number 3. Let's try something like this. So this is as hard as it's going to get, by the way. So we have 81a squared minus 49b squared. So as you can see, 81 and 49 are perfect squares. I could actually take the square root of this and get something nice, and I could take the square root of that and get something nice as well. So same thing as the last problem, the square root of 89, since I know my table really, really well. I know that 81, the square root of that is 9, and then the square root of a squared is just a. So this is basically 9a squared. And then I'm subtracting, the square root of 49 is 7. The square root of b squared is b. So I'm subtracting that squared. So it's this squared subtracted by this squared. So now that I know that it's a difference of squared, I can use the formula again. A squared minus b squared is equal to a minus b multiplied by a plus b, for what we saw earlier, which means that I can jump straight into the answer, as my factors are 9a minus 7b multiplied by 9a plus 7b. And this will be the final factored form. Again, you don't want to believe me, go ahead and multiply this out with the box. You should get the original problem. Okay, example number 4, and that's the last one that I have for you guys. Factor the following expression. So we want to factor 75x squared minus 12. Now here's the thing. For this example, if I want to take the square root of 79, I don't get something nice. If I want to take the square root of 12, I don't get something nice. These two are not in my table that I had up there, right? 75 and 12. If you could look back at the table that I gave you guys, do you see any 79s and any 12s in any of this? The answer is no, because they're not perfect squares. So what the heck? What do we do now, since it's not a perfect square? You should remember that I've told you guys in the past that the first thing that you need to do before you can do any of these problems, or doing the X and the box or difference of squares or anything like that, you need to make sure you take out the greatest common factor. Always, always, always check to make sure there's a greatest common factor. If there is a greatest common factor and you are able to take it out, you should. So now, that being said, what number can you take out of both of these terms here? So 75x squared and negative 12, the answer for that would be 3. So 3 is actually factored out of both of those things. And now we got to figure out what goes on the inside. 3 times 25 would give me 75. I also need an x squared there, and then a minus in the middle. 3 times what will give me 12? Well, the answer for that is 4. Now, that being said, okay, I already factored out the 3. Now I have to figure out, okay, is there anything that I can do to take to simplify the inside here? And the answer is yes. Again, since you're an amazing math student, you should realize that this is actually a difference of squares. We have a 25x squared subtracted by a 4, which I can rewrite as the following. So this is just 3 multiplied by 5x to the power of 2. I'm putting a parentheses because it's the whole thing squared, and then subtracted by 2 to the power of 2. So basically what this is saying is that you can actually use the difference of squares on the inside and then jump straight into the answer without having to do the x in the box. So I'm going to go ahead and write it in case you forgot. A squared minus b squared is equal to a minus b multiplied by a plus b. That's the formula. So therefore, my final answer for this, without doing very much work, yes, this 3 is still outside, so don't forget it. And then the final answer would be multiplied by 5x minus 2, and then again multiplied by 5x plus 2. So this is using the formula for the difference of two squares. Okay, so for this last example, for example number 5 of factoring using the difference of squares, I'm giving you like a trick problem real quick, because every now and then you'll get something that looks like it's factorable, but it's actually not. What does that mean? For example, if you remember from the formula for difference of squares, it says that a squared minus b squared is equal to a minus b multiplied by a plus b, right? So in this entire lesson, we've talked about the difference of squares. Difference means subtract, right? So the difference, when you're talking about the difference of something, that means you're actually subtracting two terms to be able to find that difference. Now, if you look at this problem, there is no minus between these two. And from what we can see, there is a greatest common factor that we can take out of these two. We can take a 2 out of both of these. Now, if I take out a 2, I'm going to be left with 9x squared plus 4y squared. Now, the question is, can I do the difference of squares here? Or can I use the formula if I'm left with 9x squared and 4y squared? Yes, these actually have squared roots, but just because they have squared roots doesn't mean that you can use the difference of squares. The difference of squares here says that it has to be a subtraction. In this case, we have a summation, right, addition, so we cannot do anything else after this. So don't get tricked if they put a plus between it. If you can't do it, you can't do it. That means less work for you. So you're actually done right here. So the final answer for this would be the most you can factor out is a 2. And the final answer is 2 multiplied by 9x squared plus 4y squared. Okay, thank you. I hope this was clear. See you guys on the next one.